Just when experts thought they had seen it all, along comes the James Webb Telescope to show them that bizarre cotton candy planets are out there too. But what may sound like an amusing cosmic fairy tale at first glance actually embodies a real mystery. After all, these fluffy exoplanets appear much too light for their size, pushing our current models to their limits simply by existing. On paper, everything seems so clear according to our established theories. Gas giants the size of Jupiter form when they have built a solid core of at least 10 Earth masses in the early days of their home systems. From then on, the planetary core's gravity ensures that it can hold on to a thick gas envelope, even in the face of strong stellar winds. Well, at least that's the theory. But when we look at real discoveries in space, we find exoplanets that pose serious problems for our current models of planet development. The first of these outliers was added to the star charts back in 2017. Located around 212 light-years away from us and named WASP 107b, this alien world orbits its host star in less than 6 days. The first observational data suggested it was a gas planet about the size of Jupiter, but follow-up studies over the next few years brought a rather confusing circumstance to light. Experts focused on the so-called radial velocity, analyzing the tiny wobbles of the parent star caused by the gravitational influence of its planetary companion. This method made it possible to determine the mass of the exoplanet, leading to a surprising finding. WASP 107b weighs just 30 Earth masses. In other words, although the celestial body is as large as mighty Jupiter, it only has 10% of its mass. Given this background, model calculations showed that the solid core could have a maximum of 4 Earth masses, making the planet extremely fluffy. To be more precise, this extrasolar gas giant has an unusually low density, reminiscent of cotton candy. But how could a planet with such low density even form? And above all, how did it manage to keep its massive gas envelope from escaping into space? This question is even more puzzling given that, as mentioned, WASP 107b orbits its host star at a very close distance. And while these profound questions couldn't be answered with absolute certainty, one thing seemed clear to astronomers. This mysterious cotton candy planet is an absolute outlier, a unique cosmic eccentric that turns the known mass-radius relationship of planets on its head. But if scientists at the time had already known about the companions of Kepler 51, they would have realized that such outliers are far more common in the vastness of the universe than previously thought. The James Webb Telescope revealed a surprising discovery. In terms of mass, the Sun and Kepler 51 can be considered similar, but their planetary companions are drastically different. Located in the constellation Cygnus about 2,600 light-years from us, this young star is the central star not for 1 or 2, but 3 cotton candy-like planets. The mystery surrounding the formation and maintenance of their gas envelopes is therefore threefold. To shed more light on this cosmic enigma, a research team led by Jessica Libby-Roberts of Pennsylvania State University examined the planets of Kepler 51 using the James Webb Telescope. But when they pointed the telescope at the star shortly before the predicted transit, they were in for a big surprise. The shadow cast by the planet began much too early. The researchers had miscalculated the timing, resulting in them witnessing only the end of the planet's transit. Kepler 51d passed in front of its star a full 2 hours earlier than expected. The fact that the researchers even noticed this was due to them starting their observations earlier to record the normal starlight as a reference. A slight deviation in transit time can be explained, but a discrepancy of 2 hours is another matter entirely. No matter how the experts adjusted their 3-planet models, they couldn't explain such a large deviation. It was also ruled out that the James Webb Telescope made an error, as the early transit was confirmed by the Hubble Space Telescope and several Earth-based telescopes. Ultimately, the mystery was solved by expanding the model to include a 4th planet. This celestial body apparently orbits Kepler 51 further out on a more inclined orbit. From our perspective, it doesn't pass directly in front of its host star, but its gravity significantly influences the movement of the other planets. Further analysis suggested that this 4th planet is likely a gas giant with a mass similar to its 3 counterparts. It orbits Kepler 51 on a wide, circular path with an orbital period of 264 days. This new member, named Kepler 51e, slightly adjusts the previous mass estimates, but the planets still remain too light to fit into our established models of planet formation. This is even more astonishing considering we're dealing with a quartet of cotton candy planets. Although most of these fluffy worlds appear alone in their home systems, Kepler 51 is an exceptional case. Scientists now hope to use the high-resolution spectra of the James Webb Telescope to further unravel the secrets of these puffy worlds. Aside from these cotton candy-like planets, the field of exoplanet research has recently revealed other surprising discoveries. For instance, the system around the star WASP 132, located about 400 light-years away, is home to a super-Earth, a hot Jupiter, and a distant ice giant, all in one system. A super-Earth simply refers to a large rocky planet without implying anything about its composition or habitability. Meanwhile, a hot Jupiter is an exoplanet with a mass similar to Jupiter's, but a significantly higher surface temperature due to its close orbit around its star. Interestingly, in the WASP 132 system, the super-Earth is even closer to the star than the hot Jupiter. The inner planet completes its orbit in just over a day, while the hot Jupiter takes about 6 days. Further out, the ice giant takes over 1,800 days to complete one orbit. Even more intriguingly, the star's light curve suggests the existence of another companion, possibly a brown dwarf, a celestial object between stars and planets. But this complex system raises new questions, especially about how the hot Jupiter could have migrated inward without disrupting the orbits of the other planets. Researchers suspect that the hot Jupiter's inward drift was unusually smooth, avoiding significant gravitational interactions with its planetary neighbors. However, the exact details of this gentle journey are still uncertain. If you've enjoyed this cosmic exploration, don't forget to hit the thumbs up and subscribe to our channel so you never miss a new video. See you soon.